Excellent. Thank you.
It's like this, okay?
Yes, perfect. Thank you.
Okay.
Okay,
All
so
right.
thanks
right.
everyone. Thanks everyone. So we continue with the second lecture of the day. So we have here a colleague and a friend, Jackson Levy, and he's going to talk about why modified gravity can teleparallel gravity make the situation better. We hope. Okay, Jackson, all of you.
Okay, so thank you very much for the invitation. I know the organizers worked very hard despite the global pandemic. It would have been very nice if we were all together in UNAM in Mexico, but it is what it is. Hopefully next year we'll be able to meet up after all this has passed. Yes, so following on what Jutta said, we're living in the golden age of gravitation for many reasons. Firstly, compact stars, number one, but also for cosmology. Now, what I want to do is I want to talk a little bit about, obviously, teleparallel gravity and what are the reasons for modified gravity and specifically teleparallel gravity. So today I'd like to talk about the theoretical side a little bit, and then tomorrow build on that with the observational constraints that we get from that. So obviously, what do we want to do? We want to build a teleparallel theory of gravity that's consistent observationally and internally. So it's not just enough to have a consistent theory, something that agrees with observations, such as lambda CDM. Lambda CDM, even though it as was mentioned by the previous presentation, which even if we do agree with observations, we still need to work on this to try and become consistent theoretically, and that's one of the reasons for doing modified gravity as well. So what I want to do today, as I said, is start off with the reasons for doing modified gravity, and then go into the various flavors of teleparallel gravity. How does that lead us? How does modified gravity lead us to teleparallel gravity? So the first thing to think about is, where did we start off from? So we start off with GR, generativity, from 1915, where Einstein puts together his theory of gravity with the tools he has available at the time, which was Riemann geometry, which was the Levi-Civita connection, which gives us curvature, so with no torsion, and that satisfies metricity, fine. With an energy momentum tensor that gives us a source of curvature, and that curvature for us in this geometry being taking, as we have in the picture here, taking a parallel transport of a vector, right? Later on, Einstein worked quite a bit on teleparallel gravity, in fact, and what he wanted to bring in electromagnetism. So he wanted to use teleparallel gravity by changing the connection from the Levi-Civita connection, which for most of us would be the Christopher symbols. And he wanted to use the teleparallel connection or the Weissenburg connection, where there's no curvature and that you only get torsion. And like with this graphic picture on the right, it's sort of like we're trying to close a parallelogram. So instead of a parallel transport, now we have a picture of us trying to close a parallelogram in a certain sense. With these two vectors. And Einstein gave up on this because in the end, what he found was he had designed a teleparallel equivalent of generativity, which we'll talk about again a bit later on, which is dynamically or classically generativity for all intents and purposes. And that's not what he wanted to do. So he gave up on it, and it was, in a sense, forgotten for quite a long time. So in this time period, what do we have? So we have generativity, as we all know. We have standard matter, a very successful model of the standard model of particle physics. And together, we want with these things to explain cosmologies, to explain things in the universe. So if we accept these two things, and on top of that, okay, there's dark matter and dark energy, which we'll talk about in a bit. But one big question for a long time was, does this on its own explain this picture we have here in front of us of cosmology, this history of the universe? So we have at late time, okay, with dark matter and dark energy, GR in a certain sense, fulfilling up to fairly recently a lot of the observational requirements. But the first problem and the biggest motivation for modifying gravity is not so much the late universe as such. I think you can see my cursor. Is the early universe. Is the early universe with the flatness and the horizon problems. And these things together give us inflation, which I'm sure everybody has heard of, this rapid period of expansion. So this already gives us extra ingredients in our, let's say, our standard theory of cosmology. So already we have to start adding things which aren't part of our theory of standard model of particle physics. So already we're adding the inflaton, or we're modifying matter in this sense. So giving us additions over here, right? So we have generativity here, this Einstein-Hilbert action, okay, which we have from generativity. And then on this side, besides the standard model of particle physics, now we have also this inflationary addition, let's say. So let's go to the other end of the spectrum. So let's think now a little bit more about late time. So what's happening in the late time universe? And this, again, this brings us to some modifications. So again, more modifications of matter. And in this case, starting off with galactic dynamics. So do galaxies work with GR on its own and with the things we have that we see? No, it doesn't. As we know, we need to add dark matter to this. And in fact, for a very long time, there's this slightly old picture on the right. For a very long time, people or cosmologists, theorists wanted matter to add up to the total, let's say this pie chart or this energy pie chart of the whole universe. So we say omega matter equal to 1. But then as time passed, first with dark matter from galaxies, this pie started to change quite a bit. And then later on in 1998, with the discovery of the accelerating expansion of the universe, we get the observational fact of dark energy. So that dark energy acts at late times, whatever it may be. And this pie chart bringing us to today, this pie chart here. And who knows what the future will give us from this. But so already we're starting to chip away at what we're seeing, what we know matter is made of, and our necessity of modifying matter. So having an idea of modifying what we know matter to be to fit the observations that we're making. So firstly, on dark matter itself. So there's a non-exhaustive list here, but already quite a long list of direct observation attempts over here. So there's been, over the decades, there has been many, as you would expect, attempts to try and find this so-called dark matter. In all its different variants, whether it's machos, so meaning sort of just compact objects in a sense that aren't shining, or actually new particle physics from stellar neutrinos. So there's a whole zoo of dark matter particles, but all these attempts, at least up to now, have shown no evidence, no observational evidence for having real dark matter as some sort of modified matter. Or that may change, but that's how things are at the moment. And then the other side of dark matter, of modifying matter, is that there's also another side to this coin, which is that we have dark matter coming from galaxies, so galactic dark matter. But then there's also another kind of dark matter from the cosmic microwave background radiation here on the left, which may be the same or may be different. So there's another question for dark matter, for this kind, another test, let's say, of trying to see whether dark matter is really consistent with observations. Okay, so on top of that, then we have another kind, as we said before, dark energy. So in generativity, the simplest way to bring in dark energy is as the famous cosmological constant from the two teams that were led by these three people here who won the 2011 Nobel Prize in Physics for finding the accelerating expansion of the universe. So people weren't expecting it at the time, but they found that that there is an accelerating expansion of the universe, and that for them, the simplest way of bringing this into standard theory would be through a cosmological constant. So what that means is that, again, so we have the standard model of particle physics, generativity. On top of that, to explain the early universe, we need to modify the standard model of particle physics in a certain sense to bring in inflation. On top of that, we need dark matter to explain galaxies and part of the CMB. And to explain the late time universe, we need at least a cosmological constant, this lambda. So we're sort of, we have a little bit of a patchwork of things that solve problems in different areas. And coming to the late time universe, so the late time universe was supposed to be, in a sense, okay, observationally from this so-called lambda CDM model. So lambda, the cosmological constant, and CDM, cold dark matter. So the best form of dark matter that can explain observations. And now, fairly recently, we also see that it seems there's also a problem at late times. It's still an open question whether this is really correct or not, but it seems as though that the value of the so-called Hubble parameter at current times, so the expansion rate of the universe at current times, has a little bit of a controversy or a tension in its value. So if we look again at what the two teams that found the accelerating expansion of the universe, supernova type 1a stars, through the SHOES project, or if we look at the expansion of the universe, or try to measure the expansion universe through what these guys at the bottom right did, called Holy Cow, where they looked at strong lensing by 6 quasars. In a certain sense, what these two teams did is they tried to measure the expansion of the universe in a what's called model-independent way. And for us, what this means is that they didn't depend so much on a cosmological model, on lambda CDM. They depended more on having an idea of astrophysics and other physical phenomena. Whereas on the left-hand side, we see projected values of this expansion rate at current time, this H naught, from the Planck mission and from the dark energy survey, looking at the CMB. And what they do is, by looking at the cosmic microwave background radiation, they can project out what the value of the Hubble parameter should be at present, what this should be right now. And in fact, with this graph at the bottom, one thing that you can see is that this tension in this value has actually been growing over the decades. And there's actually quite a difference. So we've got low 70s for the model independent results, and then high 60s for the model dependent. So the things from the early universe that do depend on a cosmological model to get a value of the Hubble parameter. So this again brings us much closer to why do we need to modify gravity. It's not just for consistency. It's not just because we're modifying matter, but also that there are observational reasons for doing this, observational tensions. Now, what can we do to modify gravity? And as I said, so today I'd like to focus a little bit on the theory side of how can we get to what's the basis of teleparallel gravity in a certain sense, and what guide can we use to modify gravity in general, let's say. And one nice way of doing this is through something called the Lovelock Theorem, because it gives a very nice way of guiding us, in a sense, to things we can do to modify gravity. So the Lovelock Theorem is very good because it tells us the conditions that we need to have a second order theory. So what this means is second order, meaning that we have at most second order derivatives of the metric tensor. This is very good for theoretical reasons, so we don't get things like ghosts. Also, it's good for practical reasons. It gives it's more cohesive with the rest of physics, and also the equations don't become quite so complicated. So there are many reasons for wanting this. And in Lovelock's theorem, we get that generativity up to a constant in the action, so up to its called the cosmological constant, gives us a uniqueness theorem of lambda CDM in a certain sense of generativity plus a cosmological constant. And what can we do? What does Lovelock theorem give us as the conditions to break this? So to remain second order, but also to add more things to this. So one thing we can do is we can add new fields. So instead of just a metric tensor, we can add things like scalar, tensor, or vector fields. And by and large, this is, as was mentioned in the previous presentation, a lot of people look at scalar modifications to this, like Horndeski, which I'll mention at the end again. So there's a whole host of different things you can do by adding these new fields, whatever these may be, scalar or vector, for instance, with Kroka theories, or even tensor extra fields. We can take more or less dimensions than 4 dimensions of space-time, for instance. There are predictions, but I don't think that they're close to getting to something where they can say whether this is correct or not. And something else which is still in infancy is something called where we don't start off from an action, where we have an emergent form of gravity, and there are many different very interesting ideas about how this can work, like entropic gravity, but again, it's a little bit far away from, it's not as mature as a topic as some of the other modifications to gravity. Something else we can do, like at the bottom here, is we can change the connection. And what does this mean? It means instead of using Christoffel symbols or the Levi-Civita connection, we can change this from a curvature situation to what I'll be talking about today, which is teleparallel gravity, for instance, with torsion. Or we can look at non-metricity, so f of q, if you've ever heard of it. Some other things we can do is we can consider what's called non-local terms. By and large, this looks like the inverse of the D'Alembertian. And this has some nice properties because it links up with quantum gravity, and there's a lot of nice works in this field. And then as a last option, we can give up on having second order theories and go to higher order theories. So this gives us a nice way of thinking about different kinds of modified theories that we can construct. And here we have a nice picture by the next speaker, in fact, on some of the things that people have looked at, in fact. So there's a whole zoo of modified, I mean, as physicists, whenever there's a problem, we can come up with many ideas. And here we can see some of the many ideas that people have spoken about. And teleparallel gravity, we would find it somewhere in this little box over here. So one of the many different options that are available to us over there. So what can we do to think about modified gravity? So if we are to give up on generativity, on lambda CDM, what are the options that we have for us? I mean, again, so we have those conditions from Lovelock's theorem, and we can think about many options. And the one thing that we want to do the one thing we really want to focus on for teleparallel gravity is to look for, let's call it inspiration from particle physics. And what I mean by this is we want to take a certain principle from particle physics, a gauge principle, where forces are generated by changing global symmetries to local ones. And there's a lot of literature on this. You can go and find out a lot of stuff about it. But essentially, what we want to do is we want to take this, since we have such a successful model of particle physics, I want to apply it to gravitation to see what we can get out that may be different to generativity. And there was a lot of work in this field from the 50s onwards. And in a lot of these works, okay, we get curvature, for instance, in Poincare gauge theory, which is a very large theory full of many, many pieces. Okay, there's curvature, as you would expect, but also in this theory and a lot of the theories related with gauge theory, torsion appears, but has not been studied, until at least fairly recently. It wasn't really studied in a lot of depth. But it does appear in all of these gauge theories, which is very important. And also that it appears as, its field strength appears out of the translation group. And again, there's lots of literature on what this means, but it means that it appears naturally in a certain sense. So it's not an artificial thing we add just to say we're adding something. One criticism of modified gravity is that we may, in many theories, you may just be adding something out of convenience, but I mean, it's not always the case. And over here, we're saying that this comes out naturally in a certain sense. So this gives us an option of something to consider besides curvature. So can we modify gauge gravity? Yes, we can. I mean, there are many examples as we saw. I mean, there are many examples mentioned here from metric affine, conform. There are many. And in all cases, torsion always appears in relation to this gauge structure, as we said. And something else is that torsion can sometimes ease the tension, let's say, with quantum gravity. Sometimes this hasn't been studied so much, so we can't really say so much about this. But it seems that in some cases that the tension is a little bit easier in a certain sense. And now the question is, in a sense, can we modify gravity using torsion? So there are many thousands of works on things like on this case we mentioned, but F of R and some other things like Galileo and Lovelock gravity, and there are many. So can we modify gravity using torsion? And again, so one nice thing that's always nice to come back to in this setting is to think about the famous quote by Wheeler, where he said, space-time tells matter how to move, and matter tells space-time how to curve. And in teleparallel gravity, what we do is we change just slightly the second piece, where it's true, matter tells space-time how to curve, but only if we assume the Levi-Civita connection. We can change curvature with torsion if we assume the Weissenbacher teleparallel connection. So in that case, we keep this. And what I'm trying to say here really is that the deformation we get from gravity, so whether it's curves or torsion or whatever, that this is a property, not so much of the metric or of these other things, but it's a property of the connection. So for most people, this will be the Christoffel symbols, which are an actual, the realization of the Levi-Civita connection. But there are other connections to consider. And what we want to do here is we want to go from the Levi-Civita connection, from thinking about things like the Riemann tensor, and we want to move to teleparallel gravity and to think more about, well, uncreatively, this T, which we call the torsion tensor. So how can we do this? So I don't want to give a barrage of equations, but this would be the theory section. So the first thing we can do is, before we can think about modifying gravity, we can construct something called the teleparallel equivalent of generativity. And what this is, as the name implies, as we said at the beginning, that TEGR, or teleparallel equivalent of generativity, is the equivalent of generativity, but using the teleparallel connection. So what this means is that the equations we get from this, the field equations, things, that the Schwarzschild solution remains the Schwarzschild solution, all the other things of generativity remain exactly the same, while other aspects may change. Things that come from the action, for instance, or the Lagrangian may change, but things coming from the field equations will remain the same. Now, how is this constructed? So one superficial change, I mean, it's very important, but superficial in a certain sense. So we keep, obviously, the metric tensor, but we change, when we're calculating things, we change to something called the tetrad, this E with a Latin index and a Greek index, where the Greek index is our normal index, and the Latin index refers to something called the tangent space. So instead of the metric tensor being our fundamental variable, let's say, now this tetrad will become our fundamental variable. This throws some people off, but it doesn't, I mean, unless you're working on the theoretical side, you won't even see this part. And this is sort of like a transformation between this tangent space, between the Minkowski space, let's say, and our general manifold, like if we're dealing with a Schwarzschild solution, Kerr solution, or cosmology, FLRW, whatever. Something else that this does is that this, to really write this out in total, since the tetrad is only gravitational, we have to add something called a spin connection, or this omega here. I don't want to go on to this too much because it's a bit too much into the details of teleparallel gravity. But this, in a sense, represents the local degrees of freedom, or the Lorentz group. And in any case, here on the third point, we can see our our teleparallel connection. So our equivalent, in a sense, to the Levi-Civita connection, changing this, in a sense, from Christoffel symbols, if you like, into this new connection. And something very important about this is that this connection has no curvature. So if you plug this connection into, for instance, the Riemann tensor, you don't need to put in a metric or anything like that. That will automatically always be zero because this is curvatureless. So then we need to create something new. We need to start from scratch, from foundations, and create a new way of constructing theories of gravity. And the way we can do this is through the torsion tensor. So in the fourth line here, so basically we take the antisymmetry of the lower two indices. That's basically it. And that's what we mean by torsion in a certain sense. So this will be our measure of torsion. And then by a whole lot of calculations, we can get to this torsion scalar, which I give at the very bottom here. And this is important as a scalar because it is, well, if we take our action there in the red box with the torsion scalar, that this, again, in terms of field equations, it produces identically the same thing that we have as with generativity, hence the equivalence or the TEGR. And the reason why we get this is because the Ricci scalar, which gives us the Einstein-Hilbert action, it's equal to minus t, minus the torsion scalar, plus a boundary term, this b. So when this appears linearly, it just appears as a boundary term. So we can, in a sense, throw it away because it doesn't contribute to the field equations. In fact, this b, this boundary term, is the reason why in, for instance, f of r gravity, why it's generically fourth order. In a sense, the Lovelock theorem. Because all of those extra higher order pieces are contained in that b. Sticking to f of r, if we try and think, what is the simplest thing we can do? If we want to be inspired, let's say, by f of r, what's the simplest thing we can do to modify this theory of gravity, this TEGR? Because we know a lot, there's been a lot of studies about f of r, but now let's think about this, let's in a sense, lower order, f of t, where we just add some function of the torsion scalar over here in red. And what can we say? What can we study? So tomorrow I'll talk a little bit about what this gives us observationally, but just for now we can think, what does this give us for cosmology? So if we think about cosmology, we can take the flat FLRW metric. So one of the simplest metrics we can take for flat cosmology. One of the simplest metrics in general, as in. But anyway, so taking this, we can calculate the torsion scalar, for instance, and this gives us something very simple, just 6h squared, and we can calculate the Friedman equations over here. And I write this f of t Lagrangian in this way because it's like TEGR, this minus t, plus a modification. So now we can see, like at the bottom, we can see how in red, how f of t would modify our Friedman equations. Or another way of looking at this is, one thing we can do at background, not perturbatively, but at background, we can look at this as, in a sense, a dark fluid or an effective fluid. So we can write an energy density through rho dE, and we can write an effective pressure through P dE over here. Writing these, another thing we can do, something quite straightforward, we can look at an effective equation of state. So this we know very well to be very close to -1 through observations. And we can see how this would deviate from -1 dynamically at different z's or for different functions of f for different theories. So it can tell us quite a bit, it can tell us a lot. Now, something, okay, so as you would imagine, since this is very general, this f of t gravity, you would expect there to be many models. And in fact, if you look in the literature, you'll find many, many models of f of t gravity. But there are three, just to mention the three most popular, or the three that have been probed most observationally. Power law, so the so-called Lindau model. So one thing to appreciate is, going back a bit, so t is equal to, or it's proportional to h squared. So one thing that Linda looked at is, okay, we have an exponential here, but a square root of that t. And he also looked at just a plain exponential in the third model. And what can we do with this? So again, I said that today would be mainly theory. So one thing we can do is we can look at this through a dynamical systems approach. So dynamical systems, if you haven't heard of it, it's an interesting approach which lets us, in a sense, extract a little bit more information out of these Friedman equations. Also, these Friedman equations in general are not solvable, so in closed form. So this gives us a nice way of, clinching more information from these equations. And just to give one simple example here, I mean, not to go so much into the details, but we can see the lambda CDM Friedman equations over here. And one thing that, I mean, the classic sort of textbook example of that is to take these variables down here. In fact, this is explained very nicely in this review. So on the side, I try to give all these archive links so that you can go and see what the details of some of these studies. In any case, so taking these variables over here, at least for lambda CDM, we can get out from the Friedman equation, we can get out, okay, the equation at the top line. And if we just go through this a little bit, from the Friedman equations, you can get the third point, you can get these dynamical equations. And together this forms this sort of triangle on the side over here, which tallies up, obviously, as you would expect, with our standard picture of cosmology, our standard model of cosmology. We'll go from radiation on the right to matter to cosmological constant. And we can study these points and understand whether they're stable, unstable, and how this would evolve. This would evolve exactly in conjunction with our standard model of cosmology. But what we want to do is, in dynamical systems, is to try and study these models. And again, I'm not going to go through all of the details of these because there's now a lot of work on this, at least in F of T. And what this can tell us is slightly more information on, for instance, the limits of these parameters. So if we want to have a standard picture, our standard picture of cosmology, what limits can we put a priori on these parameters? So this could help very much when we come to doing numerical simulations, because we can already start to limit some of these parameters. Like in the power law, you have got that B. If we can say something about B, it can help quite a bit in all of this. And in fact, so there's another study here where, in general, I'm not going to go through all this complicated picture here, but one thing to take away from this is that we can actually, in F of T, we can actually start off not just from a big bang, but we can also have something called bouncing cosmologies. So this is actually a nice thing because it may, maybe we can study the early universe a little bit better, and then in many cases, for just certain parameters, we can still get our standard picture of cosmology, which we would expect, or not expect, but which we would hope for. And again, it can give us very nice constraints on these model parameters. Okay, what else can we do? So besides looking at background cosmology, we can also go into the perturbative side. So I'm not sure if everyone's gone through perturbation theory, but over here, I'm just going to focus on, I'm going to talk about two kinds of perturbations. So in the first case, let's look at scalar perturbations. These are very interesting because they can be linked up with the evolution of large-scale structure, which is obviously very important in the universe and is a very important way of testing whether our models of cosmology make sense or not. So at the top, you've got the standard textbook scalar perturbation in terms of the metric. But also, again, as I said earlier, we can always write all of this down in terms of a tetrad. And we have to be very careful because we also have this so-called spin connection. But we can write this down. And through this, we can work out our normal scalar perturbations, very important. And we can get at the bottom here to our matter perturbation evolution equation, which can tell us how structures could grow in the universe. And a very important thing out of this is to take away an effective Newtonian constant, because in modified gravity, in many cases, Newton's constant can get modified slightly. So in this case, our G effective, okay, for many cases, it remains G effective, or well, for two, but it is G effective over 1 plus f, and this ft, what it means is it's our normal f of t with a derivative with respect to t. So if we were to think just about generativity, f would be 0. So this would be 0, and we would get normal Newton's constant. If we were to think, for instance, about lambda CDM, our f would be a constant. So again, this ft would be 0. It's only when we think about deviations that we start to get deviations from Newton's constant for this G effective. And just to give one example, so f of t, if we think about something called the growth factor, so here you've got the definition of the growth factor, and what it is it talks about how these perturbations grow. So in this graph, you can see how it would grow with redshift. And in this picture, what we're seeing is we're seeing the power law. So that's F1, the first model, okay, with a parameter, power 0.1. But what it shows us is that compared with lambda CDM, so the red line there, that we're within the neighborhood of lambda CDM in a certain sense. We don't expect it to be right on top because this is a different model, but we're in the neighborhood. So if there is, in a sense, a small problem, like something like the H0 tension, that this gives us some options to try and fit better that data. What else can we do? So besides f of t, can we do anything else? So I said at the beginning that we wanted to sort of generalize TEGR minus t to a general f of t, but organically or naturally, we wouldn't just consider this one scalar, just t. Another thing we can do is we can consider the boundary term b. Now b is a boundary term only when it appears in linear form. So if I were to put in, for instance, b squared or whatever, square root b or something different, this would no longer be a boundary term. So again, the second line, we see that f of t, it's not the same as f of minus t plus b. It's b only cuts off when it appears as a linear addition. And in fact, when f is dependent on minus t plus b, that is f of r. So in a certain sense, if we consider f of tb, it's a different way of generalizing f of r. And there are some generalizations of this so-called f of r theory, but in many of them, you're adding more scalars. In this case, we're actually looking at r a little bit deeper, and we're, in a sense, decoupling second and fourth order contributions, because for f of t, we get a second order theory, we get f of t. And b is the thing that gives us the fourth order contributions. So as long as b is not linear, we end up with a fourth order theory of gravity in f of tb. Okay, again, we look at this through an addition to TEGR in the action at the bottom over there. So it's like minus TEGR plus an f of tb. And so this is not quite as studied as f of t. So if there's any people interested in teleparallel gravity, this is definitely something to start thinking about, to have a look at, and maybe to compare more with observations, more studies in that direction. And as with f of t, we can write down the Friedman equations. So again, we can write this down at background as an effective fluid. So a rho effective, p effective, with their definitions down here in the middle. So at background, this looks like an effective fluid, and we can write down the equation of state. Again, we can see how it would deviate from -1. Also on the right here, you can see an example of how T and B, okay, what they mean, what they are in terms of FLRW, but also how they would add up to give us the Ricci scalar, as we know. Again, so there are literature models, but not so well studied, right? So there's still room for more suggestions and to learn more about these theories. Okay, so the first one is
Jackson, sorry, you have 10 minutes left. That's
okay. Very good. So so one thing we can do is we can so one model in literature is to take in a sense a Taylor expansion of this f of tb, where t naught and b naught would be these background values that I showed just now. And again, since B is a boundary term when it's linear, so that means that some of these things were cut off. And in fact, we can write it down here in a very nice, concise way with these A's for this general Taylor model. Then we can take, okay, a power law and a mixed power law model, you know, again, things that have been studied in literature. And here's one nice study of its dynamical systems, let's say, approach. They, you know, again, looking only at background. Okay, maybe it doesn't make so much sense to go through all the details, but something to say about this is that, first of all, the first model, the F1 model, here are some of the results of that study. It would be hard to take so much information from the pictures, but one thing that we can take from this, from studying the dynamical systems, let's say, of this model, is that this actually gives us, all the correct epochs in terms of the epochs we know from standard cosmology. Plus, this would agree with observational constraints in a certain sense. So if we use the values of observational constraints, that everything is consistent. Similarly for the other two models, but we do get some what's called phantom behavior in these models. So again, so the models are promising, but we need more studies in a certain sense. Again, something else we can do is take scalar perturbations, and in this case, so it's not quite a nice solution as in f of t. Here we get branching, so it means we get cases. Okay, the cases depend on these variables here at the bottom, but these four cases give us, okay, in the first case, branch A, so this is the majority of our f of tb, let's say. So in this case, I mean, we've got an example and we've got how our G effective looks. So again, in all these branches, we always get, as we would expect, GR and lambda CDN. But we need to think now, we need to think for each model, for each F, what do we get, which branch do we exist in? And this also makes a bit of sense. So here we have a general F of TB in a certain sense, or quite general. In the second case, we have the branch that contains F of T. So this obviously would agree with F of T, as we would imagine. As we can see in the example down there. And then, okay, we get some more in branch C. There's not so much to say about this, but it's some more cases, let's say, but not as many as branch A. And then the branch D would be this situation. So if you were to plug these variables into f of TB, you would find that it would just give you f of R. So it would give you, again, this well-known solution of f of R that we can see for G effective. So this is why it sort of makes a bit of sense, because f of TB, it behaves, we wanted to limit to f of R, but at perturbative level, it sort of differentiates a little bit into these branches. And maybe just to end off on this, I'd like to talk a little bit about something else. So for cosmological perturbation theory, something else we can look at is tensor perturbations. So the textbook example again would be the first line, where on the right hand side we see what we have for the metric, and then on the right hand side we can see how we can construct this for tetrads. One thing we get for taking tensor perturbations is this equation in the middle, this gravitational wave propagation equation. So over here, the thing to look at, okay, it's a wave equation, but the thing to look at is this alpha m and alpha t, these two parameters. So the important thing here, so h is our gravitational wave in a certain sense. And looking at these two parameters, these tell us about the deviation from general relativity. So in this case, for alpha t would be talking about the speed of propagation, whereas like alpha m would be talking about the amplitude of our gravitational wave, what we call the Planck mass run rate. And okay, we can change. I mean, maybe it's best I skip this, but basically it tells us what I just said about this amplitude and phase. And as we saw in the previous presentation, now we can actually say something about the speed of propagation of gravitational waves, thanks to the recent observation of gravitational waves, in particular the multi-messenger observation, which gives us a very, very high constraint on the speed of propagation, CT, very close to the speed of light, c. And one nice thing about f of t and f of tb is that in both cases, if you take tensor perturbations, you always end up with, first of all, with propagation at the speed of light. So organically, it's consistent with observations. And also, okay, here's one picture, one example of how the amplitude can change in some settings, but we don't know so much about what's going on over there. I think it's best to end off here, and then maybe I'll continue tomorrow with the rest of it. Does that make sense, Julia?
Yes, I think. Okay, excellent.
Okay, thank you.
Thank you, Jackson.
Thanks for your attention.
Okay, so if there are any questions, if you want to raise your hands or turn on your microphone, that will be great. Oh, yes, we have two. Che, if you want, you go ahead.
Okay, so thank you, first of all. So thank you for your introduction. So I have a question about the uniqueness of defining the tetrad or the field-bound field in this teleparallel gravity. If I remember correctly, maybe I'm wrong, I don't know. So if you have a general metric with diagonal components, non-diagonal components, sorry, and I remember it is not unique to define the corresponding tetrad, and I'm not sure whether this problem has been sorted out recently.
Yes, that's a very important question. So there is a misunderstanding in the literature about the uniqueness of the tetrad and about it whether there is local Lorentz violation. We wouldn't study it if there was local Lorentz violation. It's true that the tetrad is not unique, but we don't need this. What we need is that the tetrad, together with this spin connection, which I didn't talk about so much, that together they give us a theory which is invariant under these changes, right? And these changes, the reason why it's not unique is because, well, I'll have to go up a lot, but because the tetrad has two indices, and one of those indices is a Lorentz index. So you would expect that if you take a local Lorentz transformation, that would change. So this is something you would expect. But the important thing is that the pair, the tetrad, together with the spin connection, gives you a consistent theory, the covariance, local Lorentz invariance, and these things. So it's true that it's not unique, but it's not a problem in that sense, as long as you keep in mind the pair.
I see. Thank you.
Thank you.
Okay, thank you, Jay. Cesar, if you want, go ahead.
Yeah, thank you, Celia. Thank you very much, Jackson, for the talk. I have a kind of conceptual question because I don't fully understand. In teleparallel gravity, is the equivalence principle somehow implemented, or as a certain equivalent empirical basis as to consider the gravitational degrees of freedom as torsion?
Yes, another very important point in teleparallel gravity. So in general relativity, we must have the equivalence principle. There is no way that general relativity can survive without the equivalence principle. We must modify it somehow, right? In teleparallel gravity, we do have the equivalence principle, but it's not a necessity. So one interesting thing is that if one day we were to see some violation of the equivalence principle, teleparallel gravity would still continue to survive. But yes, it's constructed, everything I showed here assumes the equivalence principle. So we do have the equivalence principle, but it's not a necessity as it is in GR. If that makes sense.
Yeah. Can I ask one more?
Yes, please go ahead.
So if you do have this equivalence principle, are the free particles or test particles still kind of auto-parallel, or is there a force associated with it?
Yes. So one very nice thing we get in teleparallel gravity is that gravitation takes on, again, a force-like equation. So yes, in fact, out of this torsion tensor, you can build something called the contortion tensor, which acts like a force on those free particles. So in a sense, you again against a sort of Maxwell-like force equation, which is equivalent to our normal geodesic, but looks like a force equation. So it's very good in a certain sense, because we get back our conceptual picture of gravity as a force.
Thank you.
Thank you.
Cesar. Francisco, do you want to go ahead?
Yes, thank you, Celia. And thank you, Jackson, for the nice lecture. In fact, my question is related with that of Cesar. I was wondering in particular if, I mean, you have shown that these new terms and modifications, you can grade it out as effective new kind of energy density, etc. But the thing is that there are geometric terms. So far, I understand. So I was wondering about the Bianchi identities. For instance, this is not going to be the same as GR, and also about these geodesics of test particles. I mean, I think that you have not curvature, you have another geometric object that is the torsion, and I'm trying to understand the gravitational implication of this alternative way to think about gravity, in particular with the conservation of matter and energy through the Bianchi identities and the geodesic motion of particles.
Okay, so the Bianchi identities, they look different because we're treating different quantities. Now we're thinking about the torsion tensor. So they are different, but I mean, we still retain a form of Bianchi identities. And as for test particles, so again, we still get the same motion of particles, but now this motion, the reason why we get this as a force is because of this breakup, in a sense of so in GR we have inertia, non-inertia, everything is combined together, so everything is on the geometry side. But in this case now we have a slight separation, and because of this you get gravitation forcing particles to move in a certain way, which is the way that, I mean, they're equivalent parts, nothing changes there, but this comes from a force-like equation. So I'm not sure if I answered that exactly what you wanted.
Yes, just the related with the Bianchi identity. So you have a different, probably you have a different expression for the Bianchi identities.
Yeah.
But as you know, in GR, they lead to the energy conservation, the local energy conservation of matter and energy. So in this case, probably you will have some deviation of that. Can you say something about it?
No, I mean, they will be different, but they will look different, but they will give you the conservation of energy. You still keep these things. For instance, I'm talking about TEGR, for instance, the teleparallel equivalent of generativity. All of these things continue to follow. We wouldn't expect a deviation, for instance, TEGR. And then when you consider modified gravity like f of t, f of tb, and these things, you get the same things that, the same sort of deviations in certain sectors that you would get like in f of r, for instance.
Okay. Thank you.
Thank you.
Okay, thanks, Francisco. Okay, so thank you very much, Jackson. So we continue
Thank you.
with your lecture. Thank you very much.